Okay, so now that we've covered some basics with the chain rule, we're going to take it up a notch and work with some trig functions as well. So for each of our examples in this video, you're going to find the derivative. Alright, so for number 1, we're going to look at the function y equals sine squared x. And the reason I'm making a whole separate video for trig is because sometimes the way we notate it is what makes it a little bit harder. So remember, when you see sine squared x, it's not really just sin sine that we're squaring. It's sine of x all being squared. So when I see problems like this and I'm going to do the chain rule, I like to go ahead and rewrite it as that. So it's sine of x all being squared. Okay, and remember, we do the chain rule with composition of functions, so this would represent f of g of x. So that means that our outside function, f of x, would be what's outside the parentheses, so something being squared, or x squared. And our inside function, g of x, would be the sine x function. Okay, and just as a reminder, to find the derivative of a composite function, we do the derivative of the outside function, leaving the inside alone, times the derivative of the inside function. So that's what we're about to do here. So for dy over dx, we're first going to find the derivative of that outside function, or the something being squared. So we're going to use the power rule, bring down the 2. And then it would go to a power of 1, which we don't really need to write, but that's what's happening. And the sine x is actually still in there. He's not changing in that first step. Then we multiply by the derivative of the inside function. And the derivative of sine x is just cosine x. Alright, so all we have to do now really is just simplify, and there's not much we can do to clean this one up. It's simply going to be 2 sine x cosine x. And that is our answer. Alright, so not so bad. And just a hint, these are going to get progressively more complicated. So that one was great. Now let's look at our second example. Okay, so for this one we're going to look at the function y equals sine of x squared. Okay, so notice this looks very similar to what we did, but not quite the same. So we had sine squared of x. Here we have sine of x squared. And so, again, this is f of g of x. And with this particular setup, our outside function, or f of x, is going to be sine x this time. He's now the outside function, okay, because he's outside where something's been substituted. And the inside function this time will be x squared. So we've basically kind of flip-flopped our inside and outside. And we're going to see how this changes our answer. Alright, so for the derivative function, we're going to take the derivative of the outside, which was sine x, and the derivative of sine is cosine x, and we're going to leave that inside part the same, so it's going to stay x squared in this step. Then we multiply by the derivative of that, which is simply 2x. Alright, and again, we're just going to kind of combine it all together. I like to bring things like 2x or any coefficient or just plain x's to the very front of a trig expression. So in this case, I would write this one as 2x cosine of x squared. And that would be our final answer for number 2. Okay, so example 3 is where things start to get interesting. So for example 3, we're going to look at the function tangent, oops, sorry, my dinner's ready. Alright, where were we? Tangent squared of 3x. Okay, So why is this one more interesting than the previous, you may ask? Well, because there's actually more going on here than it may look like. Let's rewrite it first. So when we looked at our first example, whenever you have the powers right here, that's really the whole thing you see raised to that power. So let's rewrite that part. So it's really tangent of 3x all being squared. And you can see, maybe better in that form, that we actually have an inside of an inside of an outside, or basically 3 functions composed instead of just 2. So this would be represented as f of g of h of x. Oh yeah. So the most outside function is this base being raised to the second power, or x squared. So f of x, our most outside function, is just a good old x squared. Our inside of that function, or kind of the middle guy, is tangent of x. Woo! Okay, and then the innermost function is the 3x. Alright, so let's give this a shot. Alright, and this is one I might actually rewrite in color just to make it a little bit more easy to follow. So I'm going to rewrite the original problem as this outer function squared, and then this tangent function with the 3x inside. So I'm going to use these colors to kind of make it easier to follow. So when we take the derivative with the chain rule, we start by taking the derivative of the outside function, so the blue one here. And that's just using the power rule, and it would just become 2 times whatever that is to the first power. And we don't really need the first power written. We do need to continue to write the inside unchanged. Okay, and then we can take the derivative of what's inside of that. So then we're now taking the derivative of tangent of 3x, and the derivative of tangent is, secant squared x, again leaving that inside unchanged. Then we finally get to take the derivative of what's inside that function, which is the 3x, and the derivative of that is simply a 3. Alright, so the only thing I can really simplify here is I have a times 2 out front and a times 3 at the end. We're not distributing anything because everything is being multiplied. You don't distribute across multiplication, you only distribute across addition and subtraction. So really everything is just one giant term here. So I'll go ahead and combine the 3 and the 2 being multiplied to a 6, and then I have that tangent of 3x times secant squared of 3x, and unfortunately there's not much else we can do to make that look any prettier. That is simply our answer. Alright, so for number 4 you gotta buckle up, because this is where it gets real. So we're going to be looking at the function y equals secant of 2x plus 1 times sine of x squared. Okay, so why did I warn you you have to buckle up for this one? Well, because if you're looking closely here, we actually have 2 functions being multiplied, which means we're going to have to use the product rule. But we also have functions within functions for both of these pieces. So we're also going to have to use the chain rule twice, because each of those separate pieces will require the chain rule. Okay, so this is just going to be a lot, and we're going to take it one step at a time. That's the key here. The first thing I'm going to do is kind of write out these 2 chain rules, right? So if we look at the secant of 2x plus 1, let's see, we'll use blue for him. So for him, the outside function is secant x. Oh my gosh. Okay, sorry, I had to take my cornbread out of the oven. Alright, so outside function is secant x, inside function is that 2x plus 1 for this first piece. Alright. However, when we come over to the second piece, we have a different outside and inside function. So for this one, the outside function is sine of x, and the inside function, actually, I'm going to use different names here. Since we've already used f and g, let's be fun. Let's use j and k. jk. Inside function is x squared. Alright, here we go. It's going to be long, so you might want to give yourself some space. So dy dx. So we're going to first have to address the product rule, which says first d last plus last d first. So first means that secant of 2x plus 1 stays the same. Then we take the derivative of the last. Okay? So when I do that, I have to take the derivative of the outside, which is the sine x. That simply becomes cosine x. And the inside function is x squared, so that stays there. And then I take the derivative of x squared, and I get a 2x. Alright, so that's step one. That's the first d last. Now we need a plus, and we need a last d first. And I'm actually going to drop down to the line below because I just am not going to be able to fit it right there. But in theory, this all goes on one line. So last d first. So sine x squared, sine x squared, and then times the derivative of, secant is the outside. So if you remember, the derivative of secant x is secant x tangent x. But in this case, our x is that inside function. So, yeah, this is going to be secant of that thing, tangent of that thing. And that thing in this case is 2x plus 1 at both places. And then we take the derivative of that inside piece, which is 2x plus 1, and that would simply be a 2. Whoa, need a pen for that. Awesome. Okay, what on earth could we do from here? Honestly, not that much. Like I said, any single terms that aren't trig functions, I like to bring to the very front of the term. That's kind of standard. So I'm just going to pull this 2x out front of this giant piece, and I guess I'm just going to pull the 2 out front of this one. But other than that, that's really about it. So for my final answer, I'm going to write dy dx equals 2x secant of 2x plus 1 times cosine of x squared plus, and then again I'm going to bring this 2 all the way to the front, 2 sine of x squared secant of 2x plus 1 tangent. Oh gosh, can I make it 2x plus 1? Woo! Yes, we have reached that level. You should be very proud of yourself. That was a hard problem. I really just use this problem to illustrate that the chain rule is not that bad, but it can quickly become more complicated when it's combined with other rules like the product and the quotient rule. And being able to recognize when you need to use them is going to be the part that will take practice. And that's what we'll be doing tomorrow. This concludes our video on the chain rule with trig functions.